On board Space Shuttle Endeavour Wednesday night, the 3 astronauts of the Blue Team began Flight Day 7 of the Shuttle Radar Mapping Mission to wake up music dedicated to Endeavour's pilot, Navy Captain Dom Gorey.
Good morning, Mario. I joined the Navy to see the world. Never thought it would be so beautiful as this, but thanks for waking us up the second half of this mission.
Flight controllers have been implementing several steps to conserve propellant on board the orbiter, compensating for a problem with a small jet thruster at the end of the 200-foot mast on which several of the radar systems are located. Gorey demonstrated one method.
Good morning. One of the first things we wanted to show you this morning was one of the methods we've been using to try to save propellant. All the smart folks on the ground have come up with a couple ways to do that, and one of them is to turn off the flash evaporative system for cooling and use the supply water dump to get rid of the water instead of using that for cooling.
Payload Commander Janice Voss then showed how the crew makes certain the antennas at the end of the mast are pointing accurately.
Our system that looks at the outboard antenna and tells us exactly where it's pointed. There's the centered in the image. You can see it has a kind of a triangular shape, and that pointy thing on the top is a star tracker. And it's actually looking at the stars to give us attitude. Out the side, it's looking down the mast and at the end, which allows us to see where the outboard antenna is pointed with respect to the inboard antenna. And you can see the mast extending out along that main axis of the aorta. There's a hinge line in the top right corner of the screen, which just to the right of the screen is the C-band panels. And that hinge line is where the X-band panels join to the C-band panels, and the X-band radar actually tilts to do a little bit of pointing. So that skinny strip you see going out the top of the image is the X-band panels. And again, to help orient you, you can see off the left side of the screen is the mast going out the left side of the shuttle.
Voss said the targeting system used for the daily flycast maneuver, a method of reducing strain on the mast, is working properly.
On the rightmost tip of that, you see a plus sign. We use that as a target when we're doing our flycast maneuver, the one where we do a little pulse, get the mast to deflect a little bit, and then a larger pulse to do an orbit trim burn. We use that plus sign to allow us to precisely determine how much the camera is moving in real time. We send that image to the ground, and they can process it with video system to see how much the motion is, and it has been doing exactly as predicted.
Voss also explained how scientists on the ground will generate three-dimensional maps from the data acquired on this mission.
We actually have an interferometric pattern, kind of like making a hologram, and when you have the slightly different angles, you get a slightly different shift off the different faces, and it gives you an interference fringe pattern like you can see if you just look at a hologram without seeing the image. And you can read the spacing of those fringes to tell you the terrain height. So that's what they do. They take all this mathematical data after the flight, and they run it through software that converts that to height information.
Gorey and mission specialist Mamoru Mori spoke with the Prime Minister of Japan this morning. Mori, on his second flight in space, talked about the role humans play in exploring the heavens and the Earth.
In this Earth observation mission, in Japan, we use satellite, but this time satellite is used for manned mission, and we are using a large mast for this effort. And of course, this requires the presence of human beings. So the space station, just like the manned space mission, will be very important for the Earth observation.
Mori also demonstrated some international culinary ingenuity, slicing a tortilla in the weightlessness of zero gravity. After 8 hours of sleep, the Red Team was awakened by Mission Control Thursday morning to music dedicated to mission specialist Gerhard Thiele of Germany.
Good morning, Endeavour. Good morning to the Red Shift, and specifically to Gerhard.
Good morning, Chris. What a way to wake up to the Karelia suite. It is just wonderful, and it's great to look forward for another day of mapping.
After days of searching for solutions to propellant conservation to maintain a full mapping mission, Mission Control called Commander Kevin Kriegel with some very welcome news.
The bottom line is we have found enough cryo for a nominal mission and protect for wave-off cases. Let me tell you what went into it. As you know, we changed the water dump plan. That bought us a little cryo, opened up the dead bands. Yesterday when I had you change the notch filters, that in fact helped save some prop as well. And we had worked it to that point so that we had enough prop for all of the mapping, but we did not have prop to protect for the full wave-off cases. The problem in the wave-offs was we could not rotate the vehicle around enough to keep the thermal environment for the payload and for the tires and the rest of the vehicle. So folks worked here extensively to try and come up with a wave-off case attitude timeline that would protect the vehicle thermally and the payload as well. And the way we found the prop for that was to delete trim 8. Guys in the front row here have been working real hard on everybody to predict where we're going to be, and we are happy that we can comfortably delete trim 8 and still get good science. So by doing that, we now have enough prop for taking data right through 9 days, 9 hours, as we'd hoped, and then still have enough protected for the EVA stow, if that were required, and also for a 2+1+1 wave-off case, so 2 attempts on the first day, and then a couple more day attempts to come back as well.
As Endeavour circled the Earth every 90 minutes, the astronauts continued their work on the first human spaceflight of the 21st century.
Endeavour Houston, reveille, reveille, all hands reveille, heave out and trice up, turn 2, commence ship's work.
Good morning, Mario. I joined the Navy to see the world. Never thought it would be so beautiful as this, but thanks for waking us up for the second half of this mission. Second question is from Shannon Rector from Sparta, North Carolina, age 15. The question is, what kind of training techniques do you have to go through in order to go into space? And Shannon, after we get selected as astronauts, we have people of many backgrounds. There are test pilots, doctors, physicists, chemists, all types of different scientists. So we all get to learn a little bit about what each other do. We learn about the stars. We learn, of course, about the space shuttle, about the space station, and we also learn about high-performance jet airplanes. It takes anywhere from a year to 2 years to get through the basic training in order to become an astronaut.
And Mario, we have one from Keelan Hamilton from Houston, Texas. When SRTM is over water, is the sea surface height being measured, or is there any imaging being done? We're actually not imaging the surface of the water, but we are using the water for calibration runs so that we can calibrate the rest of the SRTM for the surface of the Earth.
Okay, what we're doing now, we've got 4 supply water tanks on the orbiter, and we're dumping out of 2 of those. We keep the alpha tank full for potable water for the crew, and we're dumping out of tanks B and D, and when the lighting is just right, that water is a spectacular sight, especially out the side hatch window right next to the WCS. It looks like an unbelievable blizzard when the sunlight's hitting it just right, and you can see how it's paralleling the mast. We haven't had any problems with the water dump interfering with the radar system or the mast.
So here's a model of a basic hardware that we have in the payload bay. We have the main antenna, our transmitter receiver here, and then we have the receiving antenna that gives us this 3D map out here on the outboard of this 200-foot or 60-meter mast. I'm going to show you this in the model to give you an idea of the big setup, and then we're going to cut away the payload bay camera so you can see it, how it actually looks in the payload bay. The first thing we're going to look at is this main antenna in the payload bay. The white section is actually an L-band system that we're not using on this flight, this big white section. What you see here in blue is the C-band radar that we're using to make the complete map. And this little black spot you see in the middle is the tracking stuff that Don was referring to. It has some star trackers on it that help us follow the payload. And Mario, I guess I will let you guys do this. It's probably easier for you if you could switch to the Charlie camera. Okay, as you see in the center of Charlie camera, there's a sort of a triangular shaped thing that is fondly known to us as Lumpy. That's the little black dot that was on the model. And it's our antenna system that our system that looks at the outboard antenna and tells us exactly where it's pointed. There's the centered in the image. You can see it has a kind of a triangular shape, and that pointy thing on the top is a star tracker. It's actually looking at the stars to give us attitude. Out the side, it's looking down the mast and at the end, which allows us to see where the outboard antenna is pointed with respect to the inboard antenna. And you can see the mast extending out along that main axis of the aorta. The big white stuff that you see is the main L-band panels on the antenna, which support all the structure on this flight, have been used on earlier flights for doing mapping. Okay, if you look at the main and inboard antenna, you can't really see it here. I'm not sure how well you can see it, but along this edge is a little tiny strip of panels called X-band. And if you go to the Bravo image, we'll see that for real in the payload bay. We are radiating both in C-band and in X-band. Okay, if you look in the image, you see there's a hinge line in the top right corner of the screen. What's just to the right of the screen is the C-band panels. And that hinge line is where the X-band panels join to the C-band panels, and the X-band radar actually tilts to do a little bit of pointing. So that skinny strip you see going out the top of the image is the X-band panels. And again, to help orient you, you can see out the left side of the screen is the mast going out the left side of the shuttle. Okay, so that's the last little piece. We just finished looking at the inside of the payload bay. We looked from one camera looking this way, the other camera will look down the X-band. Now we're going to take a camera here that's going to look down the mast and out to the outboard antenna. If you want to take Alpha camera, Mario.
Going to Alpha. We've got the image.
Okay, there you can see the mast coming out the side of the shuttle, and all the way at the tip is that outboard antenna that's a little bit smaller so that we can get it outboard, but has both the C-band and an X-band system on it. And there you can see it. It looks a little bright on this image. You might want to iris down a little bit. On the rightmost tip of that, you see a plus sign. We use that as a target when we're doing our flight cast maneuver, the one where we do a little pulse, get the mast to deflect a little bit, and then a larger pulse to do an orbit trim burn. We use that plus sign to allow us to precisely determine how much the camera is moving in real time. We send that image to the ground, and they can process it with video systems to see how much the motion is, and it has been doing exactly as predicted. So those are all the major components of the system on this flight. If you want to come back in cabin, we're just about done here. And this has been working absolutely superb. The mast has been doing a fine job. It's the largest structure, rigid structure we've ever had deployed in space, and it was a great job by AC Able and the folks at JPL in getting that mast to work so well for us. The radar antenna is doing great, and we're hoping to bring back a good map for you.
First of all, congratulations on the successful launch. Several delays were there in the schedule. However, I am very pleased to see you active and healthy while in orbit. I saw you on TV. Your main job, making the map of the Earth in a 3D fashion. How are you working over there? Thank you, Minister. The work has been going on very smoothly. On my left is the pilot Goli. The position of the space shuttle is very important for this mission, but he has been very well trained, so he has been piloting very well. Good day, Mr. Nakasone.
Good morning, Endeavour. Good morning to the Redshift, and specifically to Gerhardt.
Good morning, Chris. What a way to wake up to the Karelia suite. It is just wonderful, and it's great to look forward for another day of mapping.
I wanted to ask you first off, what is the objective of this particular mission?
Well, this mission's primary objective is to map the Earth with a three-dimensional radar system that we've got on board, and that system includes a 200-foot-long mast that carries a outboard antenna, which receives, along with the main antenna in the payload bay, dual radar returns from the Earth, and with that, essentially looking at the Earth in stereo, we can build a 3D image with all the data we're collecting.
As far as this 3D process, can you elaborate a little bit more about how it works?
Well, unfortunately, it's a lot more complicated than it sounds. We actually have an interferometric pattern, kind of like making a hologram, and when you have the slightly different angles, you get a slightly different shift off the different faces, and it gives you an interference fringe pattern, like you can see if you just look at a hologram without seeing the image. And you can read the spacing of those fringes to tell you the terrain height. So that's what they do. They take all this mathematical data after the flight and they run it through software that converts that to height information.
Now, what will be the benefits of all this 3D mapping around the globe, and about how much of the globe are you actually mapping out with this mission?
So far, we observed 70% of the total mapping area. And with this map, for example, you can fly just like you or the bird's eye view everywhere in the world. So, for example, if you go hiking or mountain climbing, not only the distance but also height you can measure precisely.
This is Mission Control Houston, back now with continuing coverage of the STS-99 shuttle radar topography mission. As the Space Shuttle Endeavour orbits the Earth right now at an altitude of just under 146 statute miles. It's making a northwest to southeast track that soon will take it over the northern coast of South America as the radar once again images the area of the tropical forest there that provides much of the oxygen for the world's atmosphere. Flying directly overhead of the Amazon basin. Again, the red team is on duty on board. Commander Kevin Kriegel, Mission Specialist Janet Cavandi, and Mission Specialist Gerhard Thiele of the European Space Agency, continuing to watch over all the shuttle systems and make sure they provide a stable platform for the collection of three-dimensional mapping data of the Earth's surface. The blue team of pilot Dom Gori, Mission Specialist Janice Voss, and Mission Specialist Mamoru Mori of the Japanese Space Agency is in its sleep shift, scheduled to wake up in about 3 hours and 48 minutes. Again, all of Endeavour systems working very well as the two radar antenna sets, one in the payload bay and one at the end of a 200-foot-long mast, continue to take images of the Earth's surface. Again, we do have a special guest with us in Mission Control today, Dan Bursch, who was an astronaut on the Space Radar Lab Mission 2 in 1994, October of that year, as two shuttle missions took a look at the Earth's surface with imaging radar for the first time, really a concerted effort to look at the Earth in two different seasons. Dan, you talked a little bit about that mission and what it was like to be on it. Tell us a little bit about perhaps what you may have heard about what happened with the research that you did on that mission.
Yeah, thanks, Kelly. What I found out was that since the time that we flew that mission in 1994, over 100 scientists have used it for the research, or it's more than 100 scientists. It's hundreds of scientists have used it for research. It's been presented at hundreds of conferences. I brought with me today just one of the 350 publications that have been produced. This one happens to be with the Journal of Geophysical Research, but this is just an example of one that they've been able to use the data. And the one thing that fascinates me about the Space Radar Lab data is that even today I was able to log on to the internet and look at some of the data that had been produced, some of the images. The images are still available for anybody to use for research, as these will be from the SRTM mission. And it's kind of incredible to me to think that even my daughter, who's 15 now, that in near future could end up using some of this data maybe for her thesis or future dissertation, or even in high school. We have thousands of educators that are also using it. So some of the other examples that I found were there's actually a place called an Angkor Wat in Cambodia was the site of some ancient temples that existed hundreds of years ago. And what I looked up is that it was an ancient complex that dated back to the 9th century. And what was interesting was that through an 800-year period, somehow 1 million people that used to live and flourish there, this complex grew, it flourished, and then ended up basically vanishing underneath a rainforest canopy. The beauty of radar is that it was able to look through, in the longer wavelengths, to look through the rainforest canopy, and they even found some possible archaeological sites for parts of the city that they never even knew existed. So if you think of a radar as looking at things from a different angle, from a different point of view, from a different spectrum, sometimes you can tell things about our planet, about anything, if you just see it in a different light. And that's basically what the radar mission is doing.
You probably saw that same area from out the windows of the shuttle when you passed overhead, and you couldn't discern those kinds of things.
Yeah, exactly. I mean, when we flew over there, basically dense canopy. It looked like a rich, fertile area, and much the same color except for the mountains. So there are many examples how you couldn't see any difference, especially when the most remarkable differences is when we would fly over the desert. And you'd fly over the desert and there's nothing but sand. And then you look at it in the L-band that could actually see a couple meters underneath soil. And here are all these drainage patterns that existed thousands and perhaps millions of years ago. So one of the just in the field of archaeology that these are being used is that they're looking for possible sites that could have existed, because a lot of times when you can look under the surface of let's say, the dry soil like a desert, you can see what we call communication lines of communication. Basically, roads existed then. People traveled across then. They left things there. It can end up showing up on an image, something that you can't see with the naked eye, but you could walk right by it, or it might be underneath the soil. So one of the big promises is in archaeology and also in mineral resources, looking for possible sources of other minerals. The shapes, geological features of the Earth can eventually lead to perhaps different sources of different minerals. One of the other areas that I saw that the data collected in our mission was being used was to develop a vegetation map of an area in Central Africa where gorillas live, and unfortunately it hasn't been. Let me make sure I get the name right, but it was near a volcano called Karasimba, and they're endangered mountain gorillas that live there, and the climate and it's a bamboo forest that ends up is basically how they live, and the shape of the bamboo forest comes out just perfectly in the radar. You can't see it really with the naked eye, but it comes out just in basically black and white with the radar. And so researchers have used that to produce a vegetation map, and eventually when it gets a little bit easier for people to travel there and do more research with them, they'll be able to do that with much more detailed map and to see how their habitat is doing there.
Now, one of the things they're telling us about this mission is that it's mapping areas that have never been mapped before. Maybe you can give us a perspective. For example, in South America, there are a lot of areas that they do not have very good terrain elevation information simply because it's always under cloud cover, and even aircraft can't fly over and do photographic imaging as we've done with mapping over many areas like the United States. You've flown over these probably in aircraft and on the shuttle. Can you explain what you can see from on orbit and how that compares to what you get from the mapping type of data?
Yeah, just from radar itself, one of the beauty of radar is that except for maybe a very, very strong thunderstorm, radar can see right through the atmosphere. It can also do it day or night. On the shuttle, of course, if it's at night, really the only thing you can see with the naked eye would possibly be the lights of cities, if it doesn't have to be cloud covered. If it's cloud covered, you won't see those. Of course, you see the thunderstorms and the lightning from the thunderstorms, but you can't see anything underneath it other than you know that the people underneath are probably having a tough day. So the beauty of radar is detecting changes, can do it day or night, and in any kind of weather. The biggest difference of SRTM is that they are mapping nearly the entire land, nearly all the land mass that's on the Earth. For SRL 1 and 2, we didn't do that. We had what we called, it was about 19 super sites, areas that we covered, made sure that we covered, and then others, it was as we went along the path. Also, the radar, the swath of the radar when we worked it, we didn't use a ScanSAR. We tested the theory, but we didn't use a ScanSAR, which covers a much wider path or swath across the ground. So using that, they can map the entire, almost the entire Earth, and the concentration is not so much on differences on the Earth.
Go ahead.
Okay, Tom, we've completed changing out the tape in the MAR PHRR X-ray 7.4 came out, and X-ray 7.6 went in at 6 days, 6 hours, 39 minutes, and we've now unpowered the MAR once again.
Thank you, and we see PHR4, the MAR recorder, X-ray 7.4 out, X-ray 7.6 in at 6:39.
That's a good copy, and the TSID after formatting was 265.
TSID 265 on the new tape, and the MAR's powered down. Good copy.
Good copy.
Okay, so Dan, that was some information going back and forth between the crew and the crew interface coordinator in the Payload Operations Control Center about the latest tape change. A little bit later, maybe we can talk some more about what it's like to be managing all those tapes on orbit, but tell us some more about what you were explaining before.
Yeah, just one of the biggest differences in SRTM and our mission, where we took a very narrow path, and percentage-wise, we didn't cover nearly the amount that they're covering now in SRTM, but the goal was different. Our goal was to look for specific changes between, over the period of about 6 months between areas, to look at the details as far as vegetation changes on the ground, looking underneath very dry soil such as a desert. Now the focus is on a different dimension, is on the 3D maps, and what's incredible is to be able to produce these 3D maps. And at first, when I saw the number on the resolution, I was a little confused, because I thought the 30 meter they were talking about in elevation, but it's not. The resolution, when they say 30 meter resolution, means that every 30 meters, just about on anywhere where you'd ever want to live on the planet, they're going to have an elevation of that point. And it's kind of incredible to think that, that basically from the goal line to the 30-yard line, every point they'll have in every a pixel, basically, of elevation every 30 meters throughout the planet, which is pretty incredible. That's a lot of information. And again, what they're collecting on the mission now, one of the things that is similar is using these PHRR recorders, the high data rate recorders that they use, and the volumes that they can record, and even one of those tapes is just mind-boggling. And
right, they have about 300 of those tapes on board, and that allows them the capacity to record about 15,000 CDs worth of information.
Yeah, it's. I can't even begin to think about, the amount of information that represents. I think we have about 200 CDs at home, and I think that's a lot. So. You were an aircraft navigator, as you mentioned earlier, in the Navy. Tell us a little bit about the potential for this kind of elevation data or altitude data for aircraft operations. We mentioned earlier that they're going to be imaging areas over South America that really we don't have good elevation data on. Is that a danger to pilots who might have to fly over those areas? Yes, it is. In fact, I've lost very good friends of mine have flown into mountains before during training missions, and most of the time we do these missions in areas that are well known. We have good elevation maps on them. But one of the accidents I remember, in particular, happened in Central America, where the amount of data that they had wasn't as good, and that could have been a factor that contributed to their accident, is not having as good a data as they could have had about the elevation of that area.
And then another thing they'll be able to do with this data is provide better models for the simulators that pilots use to train on. And you've, I'm sure, flown in simulators before.
Go ahead, Janet.
Yes, with all the confusion today, I just want to verify the tape change here for PHRR3. Do you want us to change the X tape in PHRR3 at this time?
Yes, we concur. We would like you to change the tape in PHRR3.
Okay, we'll do it. Thanks.
That was Janet Cavandi talking with Tom Farr, the Deputy SRTM Project Scientist, about the tape changes we were just discussing. But anyway, back to what we were talking about is the use of this information in simulators. You've flown in simulators. How good are they now, and how much better do you think this information will help them be?
This information will be incredible. Essentially, anywhere that you go in the world, whether it's commercial or otherwise, now they will have a database that basically is, if it's electronic, easily transferable, and you'll be able to essentially fly your simulator anywhere you want to throughout the world. We all know of aviation accidents where they've happened, where perhaps air crew wasn't quite as familiar with the terrain as they should have been. This is, I think, is just incredible how they'll be able to turn around these images and eventually use them, and just about you could fly your simulator anywhere you want to in the world. So that is just one of the many applications that we have for the digital terrain data and the 3D maps. And it would make it so much better because not only do they have the elevation data, but you do get other information from the radar as well that would give you more detail as far as, so it would make it more realistic. So it's not just seeing where the mountains are, but it makes it more realistic when you fly in the simulator to know, some of the cues as to, of course, they may have to add some information if it's at night. And there we see them, just like on cue. So, so it's very helpful. Anything that you can do, there's an expression to say, train as you fly, and that's basically if you can train somewhere where you're not, and one of the biggest things now is training for flying in airplanes is expensive. Flying an airplane is expensive. The time for the airplane, the time for the fuel, and if you can do it flying in a simulator, the simulator. The training that you get is only as good as a simulator, and in most cases the visual scene that you get, if we can make that visual scene greater, the closer it'll feel just like being there for real.
Now, I'm sure there are people out there who have been at amusement park rides that have the video screen now in front, and you're ushered into basically what's a small movie theater, and they run you through these kinds of movies. Is that a little bit what it's like to be in a simulator?
Well, one of the interesting things is that our eyes are very key to making us feel somewhere. One of the examples I can probably give, even if somebody wants to try it someday, is that one day I was actually I was at home and I was on a life cycle. And I was on the life cycle while I was playing a video game at the same time, just on the TV. And when this particular video game, when the car went over a ramp, I actually, as I was riding the bike myself, it was just watching that, felt like I was going over the ramp, and it was a very strange feeling. But it just tells you how closely a tie there is between what we see and what we end up feeling. So one of the things that's important.
Go ahead.
Yeah, Janet, we called up the Interconnect tank switch earlier. The window to get that done is going to close within the next 5 minutes. So if we can get that executed, we'd certainly appreciate it.
Okay, Mario. Thanks for the reminder.
Dan, that call was from Mario Runco, the spacecraft communicator, talking to Janet Cavandi about an interconnect switch that's going to be done on board. Can you tell us a little bit about what that is?
Yeah, basically what you do when you do an interconnect tank switch is we have different sources of fuel for the reaction control jets on the space shuttle. And what this does is allows us to use the fuel that would normally be used for the orbital maneuvering system, which are the bigger engines that they'll need to deorbit. It uses the fuel from those rather than the reaction control jet tank. So essentially, it uses some of the propellant that you won't need later on in the flight and allows you to interconnect it with reaction control jets. I've even heard that there's talk of someday of even having a interconnect where we can do that with a forward reaction control jets. Right now, there is no connection between the jets we have in the forward part of the space shuttle and the jets in the aft part. And many missions end up being critical because of just the amount of propellant that they have in the forward reaction control system. But if we can...
We'll go for depth 3.
Endeavour Houston, affirmative.
So if we can use... many missions would be helped by that case if we can use the fuel from other tanks. So essentially, it's you're just using it from different tanks.
Okay, but we were talking about flying simulators and being able to better practice your flying, and you mentioned that you're flying only as well as you go through your simulations and you train.
Right. I think probably most everybody's had some of the advances that even just in home video games that you've seen these days is kind of incredible. I mean, when I was going through high school, the biggest video game was something called Pong, I believe, and that was pretty high tech then. And of course that there really wasn't much simulation there other than you moved. It was pretty much two-dimensional. Now these video games are incredible. The 3D, the third dimension really adds a lot to the picture, and it makes you feel like you're there. So the closer that the simulator can make you feel like you're there.
Sorry for the delay, but we show ourselves complete with the tank switch and repressurizing the left domes.
Thank you much. We concur. Appreciate it.
And maybe the way to illustrate it would be perhaps someday we'll have the holodeck where you can train and everything basically looks real, and that I don't think that's too far off, but as we get better and better, and simulators are used widely these days. I know for pilot proficiency, I believe it's about half of their flight time that's required can be done in simulators. So the better we can make those simulators, better it feels like flying. It's safer. It's a great learning tool, and you can just about eventually do it anywhere. So
you fly a lot of simulations for the shuttle missions, but we have very good information about the areas that the shuttle lands in, and so it's not as critical to have some of this additional mapping data. Where it really becomes valuable is in remote areas, I would think, where people are not able to get that kind of good data until we have these three-dimensional maps on the Earth.
Right. I mean, if an expedition wants to go to some remote area of the world, they can pull up this 3D map, be very accurate as far as what's there, what kind of terrain that they can expect, what they can also get from the radar, just from the scatter data that they look at the radar. They can actually tell what kind of terrain, how rough is it, can they go there. So I can't help but think that it's going to make the job much safer, and be able to, so long as we can send an aircraft there, make it much safer.
I suppose you could even get to the point where you'd have the CDs of information on board in the cockpit and be able to practice your landing before you go actually perform it.
Yeah, and that's it's good that you mentioned that, because right now on Space Station we are looking for ways that on board that we can train, whether it's using robotics, whether it's going out on an EVA. When we're on board Space Station for 4 to 6 months and sometimes greater than a year, we're going to need to have some way to train. We won't be able to just come back to Houston temporarily, use the NVL or to go in the water in a suit to train for a spacewalk. We'll have to do it there on orbit. So eventually I do see using the simulators that we do here on Earth, but having them perhaps it'll be a laptop based, but having something similar to where we'll be able to train on orbit. But you're exactly right about be able to carry on a CD instead of having a row full of maps and charts to look at it. You can have a CD, and not only can you look at the terrain, you can just fly over it someday at whatever profile you're going to do that day.
Let's get back a little bit to the Earth sciences aspect of this mission. You were mentioning earlier to me before we started this that you had seen some interesting information about volcanoes and craters, and I remember that you took some spectacular video of a volcanic eruption on that STS-68 mission in 1994. Would you tell us about that a little bit and what you saw later and how you compare those two things between the radar version and what you saw for real from orbit?
Yeah, we it was fortunate for us, but unfortunate for the people who lived in near the Khrushchevskoye volcano on the Kamchatka Peninsula. But when we flew in 1994, there was an eruption there, and I remember vividly getting a call from the ground that, hey, we're coming up against this volcano. We know it's just erupted. Can you get some shots? And we were 500 miles away, and we could see the volcanic plume coming from it right away. So we grabbed our video cameras and other cameras, took as many pictures as we could. One of the things that was fascinating about that whole eruption was that on a matter of a few days, they had a fresh snowfall, and it was hard to tell that they even had an eruption there, because the ash had all gone away. The ash that we could see was going up to probably 60,000 feet up into the atmosphere. It was just tremendous, and it was being carried by the jet stream hundreds and hundreds of miles to the east.
And this was in October in Russia, October. So it's not that unusual to get a fresh snowfall.
Right. It was in October, and so several days later, you look at an image, and it's covered with snow, and you would hardly know that anything happened there. Now, of course, the people who lived there, they knew that something happened there, but with the radar, they took the data to process, and it was very easy to pick out, what was a fresh lava flow, what was an older flow. What we found is that the smoother rocks tend to be the older rocks because they've been eroded. The sharper rocks tend to be some of the new flows, and it's not always the case, because sometimes in the lava flows, the newer flows are the smoother ones. So that's why we needed people on the ground to look at the what we call the truth data and to tell us what was what. But so you get a different return from the surface depending upon what's there, whether it's a fresh lava flow or even the type of lava flow or the type of rock that was on there. So from that, we could tell what was a newer lava flow and what was older, and that's the type of changes that we're talking about. Even from the vegetation with the radar, you can see differences.
And that has a bearing on the people that live in that area, because I would suspect because the newer areas probably are more prone to things like mudslides that happen after eruption.
Right. One of the things I talked about earlier was in Mount Pinatubo, in particular, that these ash and mud and water flows are still displacing people. One of the things that I think will be very helpful with the SRTM is that not only do you have now a two-dimensional picture before where we could see changes, it was very obvious to look at the pictures, to look at one picture next to the other, and you could see the change in that picture. But now, if you have a 3D map of that area, you can not only just look at the change.
They were used in 2 minutes to the ZOE. We'll pick you up on the other side at 7:17 after an 8-minute gap.
And Maya Runco letting the crew on board know that we're about to lose contact. Through the tracking to realize satellite system here on the ground. That means an opportunity for the mission control folks to take a bit of a break because they won't be getting any calls from the crew. Dan knows that it's probably nice on board when you know you're not going to get a call from the ground too.
Right, but communication is good. So again, no pun intended, but it really does add another dimension to looking at changes, because now between the two flights in 1994, we could dramatically look at the changes that had gone on. If you have a three-dimensional map, then you can look at, which way should it be going? If you look at a 3D map, you ought to be able to, we can figure out, which way should the flow be going, because it all depends upon the terrain of the area.
And so you could conceivably move people out of harm's way, for example, if you suspected that there was going to be a mudslide because you had a major storm coming and you knew the direction you would expect the mud flows to go.
Right. I would expect that you could come up with a figure that says, if this rainy season, if you end up getting more than 15 inches, we predict that, this area on this side of the valley or whatever is going to be the next one to be affected. So you can move people a little bit earlier to the fact and move them to a different part that wouldn't be affected by that slide.
You also mentioned to me some interesting images you had seen about the craters, and we've been talking a lot on this mission about craters that are being imaged from on orbit on the Shuttle Radar Topography mission. You saw some also on the SRL missions. Tell us a little bit about why those are important.
Well, the craters are obviously from meteors and hitting the ground and impacts, and one of the things that the radar can do is, like I said, at least on our mission with the longer wavelengths, if you could look under a desert and look several meters underneath, many craters we can see with our naked eye, and basically it looks like concentric rings. There's a lot that you can tell from those craters. Sometimes they end up being confused with maybe is this the remnants of a volcano that used to be there. Some of the ways that they tell is they actually look at things that were maybe thrown out from the crater many miles away, and they can tell if it looks like it came from the center of that area, then they know it's probably a crater and not a volcanic field. But one of the areas in Africa that they're looking at is in Yemen, and there's an impact crater there. And much of it has already been covered up, and if they can look at some other areas that have since been covered up with sand or been eroded away, you can look at it with the radar and perhaps come up with a model of maybe it was a string of meteors that hit that area, and to perhaps kind of looking back into the past and seeing what happened several thousand years ago.
And I recall that you guys on SRL did some imaging of the Chichiclub craters in Mexico that they think may have been the remnants of the meteors that caused the long-term winter that may have led to the demise of the dinosaurs.
Right. So it really is almost looking back in time when you can look at a lot of these geological features. Geology is something that I remember being talking about geology, and to a geologist, it's probably